Alright, should be another draft physics video presentation and such. So anyway, magnetism will be the subject. The underlying subject is nobody is willing to, those who engage in theory suggestions seem very unwilling to interact with anyone who may contend that they have got a fact wrong, or they're misdescribing the evidence, or any interrogation of the theory. They all just want to be preachers preaching their independent little religions, and no one seems willing to engage in any kind of back and forth argument or debate, or even a fight over the truth. They wish to just box ghosts, and just, yay, I beat the ghost. I declared myself the king of magnetism, and I didn't have to argue. I didn't have to defend anything, like a Ken Wheeler. I'll just talk crap, and I'll never accept any critique or criticism. I'll never, ever, ever be corrected. That's everybody falls into this category. There's not a single person with any kind of will to accept criticism, and to respond to it, to engage in some sort of battle for their ideologies, whatever you want to call them, philosophies, their theories. It's just really annoying. So, I had this little interaction with Baldy Katz. He's making these claims. I point out how his claims are just bullshit until he proves one of them. That he doesn't really do any of that kind of thing. He doesn't test them. Just proclaims them and doesn't feel any obligation to demonstrate how they've passed any tests. Just like LIGO makes its claims. Doesn't ever show you any experiment demonstrating, wow, look how sensitive our detector is. Here's some evidence. Here's some experiments we did testing it. No tests. And that's the nature of physics. It's all claims, and it's just no demonstration how the claims have any or much integrity. Anyway, so what are you going to do? So, as I have always done, I'm always looking for claims and looking for the opportunity to argue the claims, and you just can't find anybody willing to engage in any kind of debate. They're just all, sorry, cowards. There's no other conclusion. Anyway, so yes, the Baldy Cats just disappeared, right? I start making valid arguments and he just goes away, pretends it never happened. But anyway, so it's just, it's a terrible circumstance that there is so little will between people who are so assertive in their confidence that they have right answers, and they seem to be the most incapable of manning up and destroying their adversary, so to speak, or even attempting to interact with them, or attempt to disengage them with any kind of argument. And again, these aren't arguments that have to necessarily be nasty. Clearly people are, on both sides. Nobody rational could argue that, the naysayers of what I've said haven't been rude and obnoxious. Fact is that most of their rudeness and obnoxiousness I've tolerated and, talked through it and attempted to explain why I think they're wrong. But yes, how much of that you're obligated to take is pretty small, I would say. No one has an obligation to accept rudeness, especially in person. And no one's going to find where I engage in rudeness until I've been rooted upon. But anyway, we'll use a physics, an example of, what the hell? Oh, there it is. Thankfully, I could get this screen back. Phew. A little bit of a panic moment. Alright, so Fractal Woman has, she, building on Ken Wheeler, apparently trying to do it in a more reasonable manner, but it's frankly the same junk. And it's she's just as impervious to correction. When you point out things, and there's no willingness to accept what can be stated quite emphatically. So I've attempted to point out that it's just beyond any kind of argument that I can analogize magnets in a couple of different ways, and those analogies fit perfectly. They just do. So I can use oil and water. I could tell you that all of this flowing stuff has nothing to do with anything really flowing. It just has to do with what's the tendency of what does the thing see. And so the idea of what a magnet's doing, she prefaces this conversation with some, verbiage about the fact that they put ism on magnetism. Now, clearly they put the ism on magnetism because, like hypnosis or hypnotism, it's a kind of possession, right? It's magnets are possessed by this ability to attract and repel. And I would argue the simple argument is whether you see it as blue and pink or whatever, or you see it as, we call it oil and water, you could understand that the theory is that if I put a piece of water here, see, water attracts to water and water repels to oil. So if I call this water and I call this oil, you could understand that the water droplet, will be equally, the amount of attraction it has to this side, it will be equal to the amount of repulsion it feels. Well, just think of it as inverted. Obviously analogies aren't perfect, so we'll just go with this. The idea is, so obviously it's likes and dislikes that attract and repel, but for the sake of the argument, just understand it as water for this moment. And the idea is that it repels the opposite. Well, that's the truth, oil. So, maybe I'll just do this. See, it attracts to water and repels. It would have been nice if I had this all thought out ahead of time, right? Because the analogy does seem a little bit backwards. It attracts to water as much as it's repelled by one side of the magnet, it's attracted to the other side. So you could just understand it as, there's two different compulsions, two opposite compulsions. One thing's attracting it, one thing's repelling it. Let's just leave it that simple. So the idea would be is the water's attracted to other water, but it's repelled by oil. And the exact opposite's true for an oil droplet, except it's completely inverse, right? So if I put oil here, I'll get two opposite arrows. I'll get this will be attracted, and this other thing will be repelled. Well, you can't see that droplet. Well, you can almost see it. Wrong way arrow again. Alright, so that's the basic concept, and you can't destroy it with anything. So the idea is that whatever field that's around this magnet, it's proportional to that. That is, that you could argue, that it's just this idea of lines, that you could just see them as being proportional. So I could draw them like this, I could say it gets stronger as this thing gets thinner, and you could just draw that kind of shape for every location. I could just draw a triangle for every location, a little point here, here, here. So any point in space, I can define how much water is in that space, or I can define how much oil is in that space. And all you're really saying is you could figure out the magnet works this way, that if I have a location here, there's a certain amount of oil getting, and there's a certain amount of water. And so if they're equal, there's just as much oil as there is water in this little spot in space, then either oil or water won't go anywhere. It'll be equally attracted and equally repelled, and it won't go anywhere. So when there's as much oil as there is water, nothing happens. Now, I could argue that I would prefer you to understand it like photons, and I could argue that it would be better for you to think of it in terms of red and blue, you could argue, and that the things you're talking about, these things in space, these points in space, are just a mixture of red and blue. And you could say that what the thing is going to be is either a blue thing or a red thing in these spaces. And what they're really just saying is the blue thing is always seeking, okay, again, we're using an inverse analogy. It's always seeking things that are, well, we can, in this case, we can say the opposite, I think, and still be safe. So the blue thing is always repelled. The blue thing just says what is red, okay? It's attracted to red and it's repelled by the blue. So the blue thing is saying I only see red, and when I see red I go towards it. Or you could say it only sees blue, and wherever there's blue it goes away from it. So that's the mechanism. It's sitting here saying, what's this? It's measuring a temperature, and it's just kind of saying, if it's above this degrees, I'm repelled. If it's below these degrees, I'm attracted. So the idea is that it's attracted to the red. If it sees red, it's attracted. If it sees blue, it's repelled. And so you can understand that any point in space could be defined as having a certain amount of red and blue. And if it's ever purple, a pure purple, a pure mixture of red and blue, it sees nothing. So the more purple it is, the more irrelevant it is, the more one color it is, the more motivated it is to move. The more imbalance there is between red and blue. The redder it is, the more it's attracted or repelled, depending on its color. In this case, it would be repelled. And in the opposite case, right color, jackass. In the opposite case, it's going to be repelled. And that's all there is. So depending on what your test monopole is, let's say a magnetic monopole, we can just we'll keep electricity out of this and just say north-south, and we'll just create the invisible, the undefined but imagined monopoles. And what would they do? So all of the field lines are just a demonstration of where you have the intensity of the individual forces and how the two lines would blend together. So the two amounts of the quantity, and where there would be a balance to a dipole is what they draw the lines to. So the lines are completely arbitrary coming out. Each point of space can be understood that this line will go 90% blue, 80 amount, 70 amount, 60 amount. This is just an amount of blue, and the red is producing the same thing, and those lines are straight lines. So the amount of red or blue there is going out into a location is completely proportional to the thing. It can be understood as just being a line that is, this is a 90, this is an 80, this is a 70, this is a 60, this is a 50, in terms of a quantity, 50 pennies worth of red. And all you're doing is mixing, well, how much blue? So if there's 70 pennies of blue and 90 pennies of red in a location, it's 20 as the net product. Extra red, it's that much more purple, blah blah blah. And that tells, depending on what color I put there, it'll see it as the exact opposite thing. One will be attracted, one will be repelled by exactly that net product. So whatever the net difference is from the amount of blue or the amount of red, whatever the net difference is, that's how much force there'll be either towards or away, depending on what color it is. So that's the field theory. The field theory is that you could draw it explicitly as lines of force, straight lines, proportionally getting weaker by the R rule. That's all you need to know. I mean, it becomes the R cubed rule when you mix the two colors, but I just mean for each individual color. So you could think of it as just being two light bulbs, a red one and a blue one, and depending on whether your test object is attracted or repelled to the two colors, they'll behave exactly as it happens in the real world. There shouldn't be any confusion. So it's a simple mechanism that has to do with whatever field you want to put in here, the field can be dissected to be straight line distances between the two objects. Those straight lines will tell you what's going to be here in terms of a field strength. And that shouldn't be something ignored. It should be something understood, that those straight lines are the element. They're the fundamental that's causing the field location's intensity. Every single location has a distance from these sources, and these sources are going to define what's in that place in the field. What the intensity of the field will be is defined by those straight lines. All right. Enough of a premise. So, not as perfect as I'd like, but the point is all of these silly lines, these curved lines, have nothing to do with an elemental, something the magnet's actually doing. It's something that emerges out as a byproduct when you start measuring the field with dipoles, not with monopoles, but with another dipole, another little magnet. So when you use another little magnet, you'll get these silly lines, but they aren't anything elemental. They're not what the magnets, they're not showing you these real lines that are the only lines that matter, the force lines. So let's play some of this and blah, 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 blah.
And nobody thinks of it as being real. But if you think of this as ether flow, if you think of this as a fluid or flow of some kind, it can be, air can flow, water can flow, ether can flow. So
again, this idea that it has a direction, the whole point is it doesn't, because if I put the positive monopole or I put the negative monopole, the flow is in exactly the opposite direction. So flow doesn't work because you're arbitrarily deciding which way the flow is based on what color the boat is. You sort of have to understand that doesn't make any sense. I put a blue boat in, it goes upstream. I put a red boat in, it goes downstream. You can't make that make any sense as something that's elemental, that there's some sort of flow of some sort of ether. There can't be, because the pressure is exactly opposite depending on what I test it with. So there has to be more to that story. That flow story doesn't make any sense. Just as conventional physics is virtual photon. They say the word virtual photon. How can it make any sense, right? Because it's just like, no, the virtual photon does these two completely different things, right? I mean, the idea is the magnet's radiating some little photon that moves the speed of light. It hits the object somehow, and the same thing in one circumstance, like we say a photon, we know only does one thing. It hits us and it imposes on us some sort of a little bit of momentum. It hits us and makes us move out. Their virtual photon has to do something quite strange in that it's a thing moving, a piece of momentum, but somehow it makes the object move this way. It makes it move towards them. It's like hitting it with a bullet and expecting the person to move towards you, but you hit them with a bullet or a cannonball. Nothing does that. That can't be the right answer, because it clearly isn't the reality. I just changed the color of this thing and I get exactly the opposite reaction from the bullet. All of a sudden momentum turns into pull. If it's one color and it's push if it's the other. So it makes sense Newtonianly in one case, but all I do is change the case and it makes absolutely no sense at all. It's completely the opposite of what should be happening. So virtual photon is not an explanation. Unless you understand that it can't be a flow of photons, that there has to be some other way. The mechanism understands them in the opposite way, in the sense of creating differences in pressure. And that gets to Ken Wheeler. But anyway.
Just because I say flow doesn't mean I think it's water or water-like or a liquid, but I would like to say that what is becoming fluid in and around a magnet is ether. And so, I would like to start.
Right, and you have to say that the monopoles or the test objects are somehow, one of them is an anti-ether particle, unether, or something. So there's unether and ether.
Talking about this in terms of ether flow. Here's an animation that I got from the video on divergence and curl from the Science Asylum channel. And he also claims that, the flow that it's an analogy, that flow is just an analogy in terms of electric and magnetic fields. But I'd like to try and indulge the idea that there is some sort of an ether and that something is in fact flowing.
Okay, I understand. All I do is paint the boat a different color and somehow it goes upstream. I mean, what's the point of thinking it's flowing, okay, if it doesn't make any sense when I just sit there and force you to make it make sense in the two real circumstances? So there's two real circumstances. I can give you an electron or a proton. I can give you two different colored boats. And that's all they are. Somehow they're just different color. And you're saying one of them obeys Newtonian mechanics and one of them completely does the opposite. Now, that doesn't make any sense. Can't be the right answer, this flow idea. Somehow the one thing, okay, has to affect the thing differently than what the other object is put. Somehow they have to have an inverse reaction to what is coming out of both sides. Both sides are emanating a light. And the simple truth is that those two lights have an inverse effect on an object. One of them, the force is dealt with by making it go some other place, and in the other case it hits and it gets a reflection. That's the simplest way to understand it. In one case the energy goes in and it leaves in some other direction. The other case it doesn't, it reflects, and that's the difference. One of them releases pressure, moves it somewhere else. One of them forces the pressure back, keeps it in the system. One of them builds pressure, one of them releases pressure. So it's like these objects are, valves, and one valve is closed and one valve is open, to opposite things. They're one-way valves and turned the opposite direction. So there's no point in me saying one-way valves because people won't know what those are. There's a little ball bearing in there, I can move. But it only works in one direction. So stuff can go one way, but it can't go back the other way. Check valves. And they're like opposite check valves.
So this is the case of two unpaired charges. Okay, so this would be a positive charge, and this would be a negative charge. And positive charges are, by convention, modeled as sources. So you can visualize that ether is flowing out of this point right here.
So they're, the fact that they're modeled, as sources, that just means, well, we draw it this way, but we could draw it flowing exactly the opposite way, depending, again, what we're using to test. So it's clearly not the right answer, because you have to reverse it to pass the test. To pass the test with the opposite charge, the boat painted the other way, you have to change the entire flow dynamic. Doesn't make any sense.
And this is the negative charge. Negative charges are generally visualized as sinks, and so you can see the ether is flowing.
Yes, generally this just makes it easier for them to make up a story, but the story has nothing to do with the truth, because you have to completely reverse it. All I do is change the color of the thing you're testing with, and you have to completely reverse the mechanism. It makes no sense.
Into the sink. So it's flowing into the sink and out of the source. And the flow direction, now in the case of unpaired charges, okay, a source is always a source and a sink is always a sink, and there's no feedback loop getting back to the source. So what I like to do is I like to imagine that when the ether...
So understand, there's no feedback loop, meaning the two things aren't connected to each other in any way. There is no source and sink. One thing is producing oil, one thing is producing water. They're both producing something. They're both creating an environment that is either going to be dominated by red or dominated by blue. They're both creating it, and the red is in competition with the blue. The place where both particles are neutral because there's just as much oil as there is water, and both of them see the same thing, which is nothing. I don't have a place to go. I'm just as repelled as I am attracted. And this analogy doesn't do that.
Flows into here. It goes into, let's give it a name. Let's call it.
See, they can't use this. If they put a positive charge and a negative charge in there at the same time, it won't work as a model. It'll fail because the one charge will move this way and the other charge will move this way. The flow won't affect them inversely. There'll be no reason for it to. So they'll both go the wrong way. One of them will go the right way, one of them will go the wrong way. Because the underlying mechanism is wrong.
Counter space, yes, okay. So what I like to imagine is that this fluid of ether is flowing into counter space and then coming back out of counter space over here. And as long as there's an equal number of positive and negative charges in the universe, okay, this can be, as long as much ether flows into counter space as flows out of counter space, everything.
So again, let me just reiterate. If you did this as red and blue, you'd realize there's a place where it's purple. And you'd realize that as a practical fact, both red boats and blue boats can't go anywhere in purple. There's no motivation. So if I just put two test charges in that same location of opposite value, the whole thing fails. Because they'll both go the same way by their diagram. There won't be any way for it to know it's supposed to go the opposite way.
Is balanced and everything is fine. And so mainstream likes to use this visualization just as an analogy, and I'd like to bring it into more of a reality by invoking the...
Right, so they only use it as an analogy. They're afraid to say it's anything real because they know all I do is change the color of that test charge and I have to reverse the flow. I have to take the whole thing and pretend the sink, the drain is the emitter, and I have to change the cathode and the anode. I have to switch them. So they know they can't say it the way it is because they know all I do is change the color of the test charge and all of a sudden the thing doesn't work. I just switch to protons instead of electrons, and the whole background fails.
Idea of counter space. Now here's a similar video, only now instead of positive and negative charges, what we have here is the north and south pole of a magnet. Now the ether flow is very similar.
So let's understand there is absolutely no experimental evidence ever detecting any flow. I put a compass needle in there, I put a charge in there, I put anything in there, there won't be any evidence of anything called a flow in a direction. Along any of those lines. There is no current flowing in those lines. It's not there.
Case we have ether flowing out of the source, so by convention we've assigned the north pole as being the source and the south pole as being the sink. And as you can see here, the ether flows out of the north pole into the south pole. The only difference here between...
So again, I'll argue you could get exactly the same vectors, the same pointing lines you could create by just drawing straight lines from the two objects. Just straight lines of proper intensity, and it'll tell you how much there is of the substance that those, you're 2 inches away from the north end and you're 3 inches away from the south end. Well, then you're going to be decidedly more north than south. Your color is going to be more red than blue. It's that simple. Straight lines explain every one of those curved lines.
The charges in a magnet is now there's a feedback loop. There's reciprocation, bringing the ether through the magnet to feed the North Pole. So no longer does the ether have to go to counter space and out of counter space. In fact, counter space has moved here. In this situation, you could You could.
So this doesn't even make any sense, right? To use these terminologies, nothing, counter nothing, ether, counter ether. So if they would have, they want to use, like, they want to pretend there's two things, two places to go, your space and then counter space, when the simple answer is north, oil, and water. They're two opposite things that have an opposite effect on each other. That's clearly what exists. That happens in charge, right? Plus and minus and the inverse reactions of protons and electrons. It's the same as the magnet, the same inverse reaction. And there's no going from one to the other flow. There's just that obviously the more water coming out of one means that water will be attracted to water and be repelled by the oil. There's more oil on the one side and more water on the other side. Where does the water molecule go? Well, it goes to the water side. If it's an oil molecule, it goes to the oil side. You have to understand it as two forces. Then two forces aren't space and counter space. Those aren't forces. It's, whatever you want to call it, electron force and proton force, or it's north force and south force.
Say that the ether is coming out of the source, going through the South Pole into counter space, and then coming out of counter space, and then completing the loop.
Right, and if I just did this with electrical monopoles, if I could put two monopoles right next to each other like that, they would become essentially a magnet. And then how does your explanation work? You're saying protons are counter space and electrons would be space? I mean, it doesn't work. Why do the two colored boats behave exactly the opposite? How can you have a flow in a direction and then state that a boat goes up the stream?
Okay, so counter space is here in the magnet, and counter space is here and here in the case of the charge. Okay, counter space is here and here, but not here and not here. Okay, it's here and here, it's not here, and it's not here. And then
I don't even know how that makes sense. I mean, clearly the field has proportions in it, and this location and that location, there's a certain amount of oil and water. There's a certain amount of pressure that's going to push, depending on what I put in there. It's going to be attracted and repelled exactly inversely. So again, you have to pretend that somehow the particles themselves, how do they know whether they're counter space or space? I mean, how do you define them as being? How do you explain how the flow changes direction by changing the boat?
And in the case of magnetism, counter space is here, not here, not here. It's here. And the ether is flowing from the North Pole out through space, back into the South Pole, reciprocating through counter space. So it's going to counter space and then out or into counter space and out of counter space. Counter space is here in the magnet.
What do I need the counter space for? So exactly, I mean, you have it going in and then coming out as if there was nothing there. So why are you putting something there? Why do I need the counter space exactly? You already have the flow going that way. What do I need the counter space for?
So here's another image. On the left we have a positive charge and a negative charge, and we have a North Pole and a South Pole. And looking at the static diagram, you can see that the source is always a source, and a sink is always a sink.
So more nonsense, right? Because these aren't charges, these are boats, right? So these are boats, red boat tied to a blue boat. So what does a red boat tied to a blue boat do? And those arrows are just showing you what red boats tied to blue boats do. Well, no, that's still the flow crap, yeah. So that's charges. So again, it's just showing you what a red charge does. If I want to show you what a blue boat does, I have to inverse all those arrows.
And there's no connection back to the source in this condition, where you have unpaired charges that are close to each other. So ether can flow this way, but it doesn't flow back up here. In contrast to the magnet, where the ether flows,
it does flow that way if I just change the charge.
goes out here comes up here and flies through the magnet, through counter space. So it's actually going into counter space and now back out of counter space and going to the North Pole. Whereas over here, it's going into counter space, coming out of counter space through some wormhole or something. There's no direct connection between here and here in 3D space. The connection is through counter space. The connection is always through counter space, only in the unpaired charges, counter space.
So again, I don't even know how to say it. All there is in that field, there's an amount of oil and an amount of water. And you either put a water drop there or an oil drop there, and it will move proportional to how much oil or water it sees. So it looks around, it says that way is red, that way is blue. And I'm either attracted to red or blue and repelled by the opposite. So that's the way I go. And that's it. And all straight lines. Like I said, they're radiated like little light bulbs. One is red light bulb, one is a blue light bulb. And wherever you have perfect purple, it doesn't matter whether you put a red or a blue there. It'll just stay there. It won't go anywhere. There's no difference. It can't tell the difference between going that way and going that way. Neither one is more attractive or repulsive. So it doesn't do anything. And that's the test of the right answer. The right answer is there's places where both of these boats, red or blue, should go absolutely nowhere. Their model doesn't do that. And reality does do that.
Space is in a direction that we can't see. And in the case of the magnet, counter space is right there. So counter space is only here, and only here, and only here in the case of the magnet. Now, how do we turn this into this? Well, it's my opinion that...
It's just so funny that they use this concept of counter space. So counter space is some silly little line inside of a magnet. That's counter space, whatever the hell that is. And it's a place where you wormhole. And so you change something that's high pressure into low pressure, or you change a low pressure into a high pressure, I don't know. It goes in and it comes back out. Somehow it gets re-energized. So it's like squirrels are going in, and the squirrels are really tired, and then they go into counter space, and they come out really excited again. They get a little boost. I don't know.
You turn this into this by bringing the charges together and binding them in a system. So the difference between this and this is that these two charges aren't bound to each other. They're free to move around space, at their will. Well, at our will, maybe. And the magnet, the north and south pole, the positive and negative charge, are bound to a object, to a physical object. They're bound to each other.
No, the real point is that they are aligned in such a way as that all of these turns, all of these ways of negating force for the opposite thing, all the turns are the same way. So blue goes in here, comes out red out here. Red comes in here, comes out blue here. So it's all blue on one side and all red on the other side. By just switching that direction. Blue force goes this way, red force goes that way. And magnet.
And so if you bind these two, the positive and negative charge, to each other, then you can have reciprocation, because then the ether can come out of the positive and go back into the negative and go through counter space, which...
All right, so there's no evidence of anything doing any of this moving. There's no energy for it, frankly. So they describe this stuff moving, doing stuff. They don't have account in any way for where it got its energy from. The simple answer is that a magnet is just filtering gravity. Gravity is purple. It's got a bunch of red and blue, oil and water. And when it hits the magnet, the oil goes one way, the water goes the other way. It's that simple.
Now is here instead of here and here. So this is just an idea I came up with the other day. I still have to work on it. So I can show you that when you bring two charges close together, well, even when they're far apart, you have a 0 point in the middle. You have a 0 point that measures the equipotential that you measure is 0 right here at the point between.
Exactly. Just as much purple, just as much red as blue, and you get purple. Okay. Neither charge will go anywhere. No, wrong answer. In this case, I mean, obviously, the blue will go towards the red, and the reds will go towards the blue.
the positive and negative charge. And you can see that, this looks more like a magnet and less like two independent charges. So my opinion is that the only difference between a magnet and two independent charges is binding, if they're bound into an object, so this could be analogous to a hydrogen atom, where the
well, obviously this bound thing is a little bit tricky. They're both made out of atoms. Magnets are made out of atoms. Something that was charged is made out of atoms, and clearly the atoms are creating the phenomenon. Now I would argue that in the case of charge, it's just about surfaces, and with a magnet, it's about the interior of the magnet. The whole magnet is aligning, dipoles, where in the case of charge, the dipoles are all facing out or all facing in.
Positive charge and the negative charge have a boundary condition, the boundary of the atom. So here's a picture of the isopotential field that you can find and measure around a magnet. Okay, here's the magnet. Here's the what I've been calling isopotential line.
Right. So again, there's little point in having the conversation in this context, because these lines, it would be better if they did use color more coherently. And the fact is that one side is producing red and one side is producing blue, and that's all there really is. There's no isopotential lines. These again are just the lines you draw, and you say, what's the mixture of the force doing? What's the I don't even know how to say that, but nothing travels those lines.
But in reality, these are isopotential surfaces, and this is a scalar field. This is a scalar field because every point, every location in the field of view is assigned a value, and in the case of this potential, you can think it is basic.
It's just being assigned a mixture. How much red is there compared to how much blue? And that's all it's doing. But what it's also, why it's not realistic is because it's not pointing out that the intensity of the purple. So there's strong purple here, there's very weak purple the further you go out.
A voltage measurement, at least in the experiment I did, I measured voltage in different locations around the magnet, and if you measured all the locations around the magnet, you would be able to define these isopotential surfaces of equal value. So if, each point on this surface everywhere would have a value of, say, 0.06, and then this would be 0.05, and this would be 0.04, and then you can see that there's kind of an acceleration. This is a gradient. It forms a gradient. And so this depiction of a field around a magnet, of course, is different than the...
It's useless. Like I said, this isn't even showing you which way a boat goes. It's showing you nothing that has any real relevance. It's, just showing you, if I was just to draw what's the percentages of red force to blue force.
The normal flux lines, which mainstream popularized as the magnetic field. So when you say magnetic field, you think of the flux lines usually, which are here. When they say magnetic field, right away you think of the flow. You think of the flux lines, and not this field, not the scalar field.
Yeah, because this field nothing will show you this. Nothing will draw this. You won't see this ever. Okay, it doesn't happen as anything real.
Okay, and I just want to show you quickly this video to show you the three-dimensional. Okay, this is to show you the surface, that these are isopotential surfaces and not just lines or not just curves. Okay, when you intersect a three-dimensional volume, and when you intersect a three-dimensional surface with a plane, so this would be analogous to looking down the North and South Pole. So the isopotential lines, the isopotential curves around the North Pole are circular, and the isopotential...
Again, there's just no experiment that'll show you this. This is just something drawn. It doesn't have anything to do with anything that's real.
Curves around the dipole, when you look from the dipole direction, look like that. So these are contours from a slice taken out of... Let me go back to a good view here. There's a good view. So this is just when you intersect the plane of an iso surface, you get iso curves. And so in radiation therapy, they call them isodose curves. And so this is analogous to isodose curves in radiation therapy. But the isopotentials that I'm talking about, the isopotentials are...
Again, isopotentials just means the points where there's equal amounts.
really surfaces and not lines. And here's a picture of electric dipole. So this is the isopotential lines around an electric dipole, and these are the isopotential lines around a magnet, and there's really no difference. And they can be generalized to lines or surfaces of equal strength, because the voltage measurements that I made around the magnet are directly proportional to the strength, the field strength. The strength that a test particle, that a test magnet, that a test charge would feel.
So it's a huge difference between a test magnet and a test charge, right? So we know the test magnet is a red and blue boat tied together. A test charge is either a red boat or a blue boat. So there's no way she can say, oh, no matter which one I put in there, it's the same. No, it's not going to be the same.
At that particular location on the surface. Okay, so each point on the surface, so if I'm here, if I have a little ball bearing, like I showed you in the ball bearing experiments, if I put it here, or here, or here, or here, it's going to experience the same force everywhere along this line.
Right, and the ball bearing didn't travel. Again, I've already pointed out that experiment. I played that video and just forget it. There's no point in pointing out the fact that it's a complete distortion of the truth. You were using gravity to imitate a curved path, but that curved path did not match this line at all. It's just a curved line. You never showed how it's the same arc on that line. Nothing. And it wasn't the same.
So that's...
She's just doing this, it seems like, it looks like thing. That's it. You know, there's no science here.
Isopotential scalar field around the magnet. Now this field diagram is just as useful as the flux diagram. This is not better than the flux diagram. The flux diagram isn't better than this. I like this diagram because it shows me the gradient. I can see clearly the gradient of the force field. Okay, this is a field of forces, and I can see the gradient, and that will tell me, that tells me a lot about what's going on around this magnet if I place a test particle here.
Yeah, but it won't work. I'm just saying that this is a fake reality, right? This idea that you're going to segregate blue and red or put them in the same space, then they can't occupy the same space. So there's nothing that does this.
Okay, so it tells me a lot about the forces that will be experienced in and around the magnet. So next I want to talk about the similarities between the magnetic potential diagram and the electric potential diagram, the magnetic isopotential diagram and the electric isopotential diagram.
So again, we're just saying again, monopole, dipole, monopole, dipole. We're just saying tie two boats together and then see what those two boats do, or test it with individual red and blue boats. That's all.
Which are very similar. In fact, there's no difference really between these two field diagrams. Here's another.
Yes, monopole. The magnetic monopoles would look just like electric monopoles. There wouldn't be any difference between them. They would do exactly the same thing. The closer you put them together, the more they're going to look like a magnet. Period. Turn them into dipoles.
Third example, and I showed you just a few minutes ago that when you place a volt, a reading, a Hall sensor, or whatever it is to read the potential around two monopoles that are near each other, at the very, very center, you get a zero reading. And same thing with the magnet. If I...
Right. Those are where the lines are straight. Okay? The length of the line from the red is exactly the same length as the line from the blue. Where the lines are any point where the lines are exactly the same length, that's purple. And neither boat will move.
Placed my Hall sensor right here, I'm going to get a zero reading. And so in a previous video, I did this, and I placed the Hall sensor there, and I got a reading of 0.06, which is very close to zero.
You only get a reading, plus or minus, okay, based on how long those lines are. How far away am I from the center of those two poles? That's it. You just measure how long the line is. Whichever one has a longer line. If the red is longer, positive. Blue is longer, negative.
It was very difficult to find zero because it's a very small magnet, and you're basically if you look at this diagram here, it's a very fine line. It's very, very hard to get exactly zero because there's a lot of other isopotential lines close by, and so as you get closer to the magnet, you can see it changes really quickly.
Yes, the further away you are, the more a little tiny change in your movement is going to make the two distances different. So it's harder and harder the further away you go. The longer the lines are, the less difference there is in their length, so to speak, percentage wise. And the shorter the lines, the less difference in their length, percentage wise. So it's a lot easier, yes, to find the zero the closer you go.
It changes really quickly, and so you have to get exactly halfway at the dielectric inertial plane to get a zero reading. Now, Ken Wheeler says that at the center of the magnet, there is no magnetism. At the center of the magnet, there is no magnetism. Now, what does that mean? Well, if you don't have any magnetism, you don't have any field strength. And so,
so again, it was just a gravity argument. In between the moon and the Earth, you don't have any gravity. Of course, you still have gravity. You still have red and blue. You still have force. You just have an equal amount, and that's all there is here. Again, this is kind of just obviously understood. Okay, there's even between two charges, there's an isopotential line, or whatever you want to call it. Just put two charges in, and again, all the argument is that you just measure. There's a length of line that will be the same from both. Okay, both places will have the same length line, and those places will always create a zero. Okay, so you have a line where all the lines are the same exact length. The line hitting this point and the line from this hitting this point will be exactly the same length, from center to center, and therefore you'll have a perfect mixture of oil and water, and any boat that's there is just going to say, I'm not going anywhere. Whether it's red or blue, whether they're tied together or not, it doesn't matter. Boats don't go anywhere. And that's the giveaway. That's the part telling you quite clearly that this is about how the test charge reacts to what's in the field, and that both fields are producing something out. Both objects are flowing out. There is no out of one side and into the other side. There's just out. And it's either oil or water. And no matter which one it is on this line, it's not going anywhere.
the very center of a magnet, you get a zero potential. You get a zero potential. And same thing with at the halfway point between a positive and negative charge that are close to each other, you get a zero reading. And the isopotential lines, the isopotential curves, because they are in real life three-dimensional curves, three-dimensional surfaces, in both cases. Okay, so the field diagrams for the...
So again, this is not saying anything, right? It's just, I mean, it's so obvious why that line is there. Because it's equidistant, no matter what point I hit there, there's an equal distance from the center of the charge. There's just as much, again, red versus blue light.
Isopotentials between monopole charges in a dipole configuration and the magnet are identical. There is no difference. They are, for all intents and purposes, identical. So the next experiment I want to show you kind of shows you this gradient in real life being read by the Hall sensor and displayed with the voltmeter. Okay, so here is the video, and at this point right here, the voltmeter is reading 0.02, and then as I get closer to the magnet, then this changes to 0.03, and then 0.04, and then 5, 6, 7. You can see it speeding up. I'm going at the same rate. I'm not moving towards the magnet faster. In fact, I'm moving almost at a constant rate between here and here. But as I get closer to the magnet, the readings right here, so now we have 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, blah, blah, blah.
Yeah, it's an inverse square law. Right. Okay, thanks.
Quickly up to the maximum when 1.4 when we touch the magnet. And so what that is depicting, okay, I'm going to show that again. Actually, I'm going to overlay the isopotential line so you can see. And right now there's a reading of 0.02, and then when I get to the next line, it's going to be 0.03, then 0.04, 5, 6, 7, and then you can see a very steep slope here.
It's just a drawing of the inverse square law. So yeah, it's not telling you anything.
Be referred to as a slope. It's a gradient, and I know we've talked about gradients before, so I'm not going to explain that here, but everyone knows that a gradient is a slope, and a slope is like a hill or a valley. In this case, it would be
How much light you would see. So you could do the same thing with a light bulb. Same exact thing. You do the same exact experiment. Just, move a photo detector closer and closer and closer, and as you get closer, it gets more and more intense. It's a multiple effect. Based on the fact that the photons are spreading in two directions.
Possibly thought of as a valley. So like I said before, isopotential field diagrams can tell you a lot about what's going on around a magnet and around a dipole, positive and negative charge dipole. If you place an object here, for example, say a ball bearing or a small magnet, it's going to experience extremely strong force, because when I put the Hall sensor right here on the magnet, I get the highest reading of 1.40 or 1.41. But when I put the Hall sensor right here, I get a 0 voltage reading. And so the force is...
So to say putting a magnet here, obviously the magnet has to turn. If you don't turn the magnet, you'll have exactly the opposite effect. So again, this is just plain... This isn't anything that happens in the real world. So, this is just sort of lying. She's saying that she's magically made something that's both blue and red and put it in a location and it does a certain thing. Well, no, it doesn't. A magnet has always one side or the other side. If I have the blue side facing the magnet, it will be attracted. If the red side is forced to face the red side, it will repel. So this doesn't have anything to do with reality. This is just drawing pictures.
Felt right here are going to be much less than the force felt right here. In fact, if I had an infinitely thin object here, if I had an infinitely thin magnet or an infinitely thin piece of metal, it would experience no force at the dielectric inertial plane of the magnet. Okay.
I don't even think it has to be infinitely thin, frankly. It really doesn't, as a practical matter, just because it can be massive enough where there won't be enough force. I mean, there's a zero difference in the potentials, and a little bit away, it's not exactly going to be a huge amount of force. So it's not like you fall on one side and it's all automatically you're hugely attracted. So if you just use something heavy enough, the heavy thing won't move on that line.
So in this next experiment, I'm going to show you how that works. And so in this experiment, what I have, so I just want to show, North Pole is up. North Pole is up. And inside this little plastic housing here, I just have a tiny ball bearing, like the one I used in the previous video. And so you can see, okay, let me run that again.
So again, it's already known that the ball bearing magnetizes the exact opposite to the field you put it in. So it's going to point the red end of the boat towards the blue, and it's going to point the blue end towards the red. So the boat turns. And so what it's seeing is just a lot of red on red, or blue on blue, or red on blue, or blue on red. I mean, if you face the magnets towards each other, yes, it's obvious that the other ends, the blue light's not even seen, right? So if I have two magnets, the red stuff going this way, they would repel because it's all red. If the one magnet turns, which the ball bearing will do, the ball bearing will magnetize exactly the opposite. So it'll be clearly just one-way stream. It'll be all blue light on one side, all water, and all oil on the other side. So clearly the oil droplet will go that way and the water droplet will go that way.
North Pole, ball bearing, and so I'm going to bring it close to the magnet, and as you can see, I'm able to pick up the magnet when I touch it to the North Pole. Okay, so the ball bearing can pick up the magnet, no problem. In fact, I'm going to try to put it right in the middle here. It doesn't want to go there, but yeah, it stays there, and I can...
It doesn't want to. Anyway, you can do it with the South Pole too, because the ball bearing magnetizes to your preference.
And pick it up, and so I have a very strong force. I'm feeling a very strong force between the ball bearing and the magnet at the North Pole. Now, right now, I'm trying to touch it to the dielectric inertial plane. I'm trying to find that sweet spot in the middle, and it's very difficult because the ball bearing wants to fly to the North Pole, or it wants to fly to the South Pole. So if the ball bearing is just a little bit on one side of the dielectric inertial plane, it's going to go one way, and if it's slightly on the other side, it's going to fly the other way. And so it's very hard to find that sweet spot. But there it is. I was able to touch the dielectric inertial plane and lift up the ball bearing, and it does not pick up the magnet. It's only when it's at the North Pole, and of course it wants to fly to the North.
Yes, obviously. So again, it's no surprise. There's just about there's no it's all purple there, purple. There's just as much oil, just as much water. The ball bearing doesn't even know which way to turn the boat because there's so little potential difference. It can't feel any pressure more one way, more the other way, so nothing happens.
North Pole, because it is Santa Claus.
Again, not because there's a lack of force, it's just that the two forces are equal. Just like the going, the right distance between the Earth and the Moon, and you say there's no gravity there. But there really is. The Moon is still pulling you towards the Moon, and the Earth is still pulling you towards the Earth, so to speak. You're still having acceleration in both those directions. It's just that the two accelerations are in opposite directions, so you end up going nowhere. You go this way, and then you go back that way, and you just can't get anywhere.
Just kidding. So here I am touching it so now it's up against the back wall here, and I was able to touch it to the dielectric inertial plane and not pick up the magnet. But again, see, it always wants to fly toward the North Pole. But let's see, I've got a bit more time on this video, so I think in the end I'm able to repeatedly, you can see I can drag the magnet too, but there it is. Yeah, I'm actually pushing the magnet with the ball bearing. It's interacting. But again, I can go right to the very center of one of the poles and pick up the magnet.
Right, which is a surprise why. I mean, the poles are obviously one color. The sides are two colors. Okay, that's all you need to know. There's only water coming out of this end, no oil. So, and the other side, the sides, there's obviously oil and water mixing. Clearly fundamentally different things.
So what this is saying is, so when I place the ball bearing here, if I'm a little bit up, it wants to fly up here. Now, if it was a spherical magnet, that was a cylinder magnet, but if it was a spherical magnet, it would actually want to fly to here.
Alright, so there's no evidence that it wants to fly towards the north end. So that's just, she just made that part up, frankly. There's just as much potential that it flies towards the south end. So there's no evidence that it goes north and doesn't do the same thing, go south, depending on what bias you end up pushing it on.
Want to fly to the top, to the very top. But with cylinder magnets, this region here is kind of spread out, and so it really wants to fly. This actually wants to fly to the edge, but that is the edge. So if the ball bearing is a little bit up, it's going to fly this way, and if the ball bearing is a little bit down, it's going to fly this way. But if it's right in the middle,
yeah, so why
then the force is going to be
say
very
to
low.
the north?
The force is going to be very low, as you saw, and it was not able to pick up the magnet like it does when I place it here. So I found that so I find this diagram really useful because the
yeah. So but again, you should understand, well, why can't it pick it up? Oh, that's right, because there is no real attractive force. There's just pressure. It feels, and that's all there is. And so there's nothing attaching it to the magnet at that location. There's no pressure difference. So it can't pull something with it because there's no imbalance in the pressure. You have to stick to it, so to speak. You have to be motivated to move towards it, essentially, for you to be able to carry something with you.
The vector diagram, the flux diagram of a magnet, doesn't really give me a clear idea of that would happen, but this diagram clearly shows me that there should be no forces right along this line, and there should be plenty of force right at this point right here. So in this next experiment, I want to repeat what I did previously with the ball bearing.
So I'll say it again, this is not the profile of a magnet at all. The magnet is definitely lots of red this way, lots of blue this way. So if you were to really draw what you're going to get out of a magnet, you're going to get a lot of straight line blues and a lot of straight line reds in this area, and then as soon as you start moving over here is where the two colors start mixing.
By placing it far away from the magnet, but in a region where it will follow an isopotential line, only this time I'm going to use a tiny, tiny magnet instead of a ball bearing. And so here's my setup. So first what I'm going to do is I'm going to do a test without the magnet. I'm going to show you what happens when I don't place a magnet. Now you can see the magnet is very, very small. So without the big magnet over here, this tiny magnet is not doing anything. So it's not rolling away like the ball bearing was. Now there still is a slight gravitational gradient this way. If this was a ball bearing, it would roll this way. For some reason, this magnet is not rolling, and I'm actually not sure why, because it should be. But anyway, so this is just to prove that without the magnet, it does not go anywhere. It doesn't roll anywhere. It doesn't roll along any isopotential line. It just does its own thing. So there are no forces right now other than my finger acting on.
Well, I don't know what this surface is, but clearly it's not behaving naturally. So this surface must have some iron in it or something, because it's obviously not behaving normally. It actually goes and then rolls back, and you can see it wobbling. It's obviously creating. There's a mixed field in there somewhere. Somewhere there's something magnetic. I don't know what this material is you're doing it on top of, but it probably wasn't the right choice. It's probably metallic of some kind. What do I want to? Yeah. This. I mean, just to do this line thing, just to try to explain how she's just perverting lines and pretending they're real lines when they're not. They're just not real lines. So I could draw two charges, and I can understand that the field is always proportional. I'm not drawing that very perfectly. And so she's going to take these two sane drawings and try to sit there and smash them together, okay, where these lines represent how strong the force is. So let's say they're tighter in the center and they get weaker as you go out. Okay, there's more of them, so you could think of it that way. Then when she pushes them together, she's just showing how they deform based on the fact that you're pushing this one into this one's space, but they don't actually deform the way she drew them. Again, it's just about the distances. So they really do this, and they really do this. This curving in thing doesn't really exist because it's equal on both sides. So these end up really being the lines of the potential. So I don't know, is there anything else I got to say about that? But they're distorting in both directions because you're measuring how this plus this proportion. This is obviously, the red is much weaker. Its line here is much weaker than the green line here, and you're trying to bend two lines into one shape. And the two lines are two fundamentally different things. I don't even know how to say that now. But anyway, it's not an image of anything does.
That magnet. Okay, so now the magnet is in place, and now when I drop the tiny magnet here, it follows the isopotential line, and I'm not pushing it, and it's actually taking almost exactly the same path every time. So if you can watch, you can see that it's taking almost exactly the same path every time.
Okay, she says it, but she didn't. There's no calculus here to demonstrate it. It's not following that line. It does, in fact, move into stronger and stronger magnetic fields as it's moving. Its momentum is like the same momentum you would have as an Earth in orbit. And the truth is, it's just a degrading orbit. It's not following any precise mathematical line, because every time you're rolling it at a different velocity.
So now what I'm going to do is I'm going to replay that, only I'm going to place my exponential lines, and you can actually, I'll do this a bunch of times, you can watch that every time I do this, it follows the isopotential line. Until it gets up to here, it goes all the way along the line until it gets to about here, and then it flies up.
Yes, because so that should be a clue that this is just, again,
the North Pole is actually facing me. So just
this is just more. It looks like, it has nothing to do with reality. So again, she didn't even roll it. She couldn't even show us it rolling in the first, which seems kind of bizarre. She couldn't get it to roll across the table. Now, all of a sudden, it is rolling across the table and you just let it go? No, she's obviously pushing it now.
For perspective, my camera is on, this is a tabletop. There's all the magnets that I collected. This is a tabletop, and my camera is facing down. and the magnet is over here, and the North Pole is facing this way, and so the North Pole is facing this way, and the South Pole is facing away. So this is exactly what I did in my previous video, only I used a spherical magnet instead of a cylinder magnet.
And again, you could do it with anything as long as you adjust your drawing to the slope of the table, your gravity.
Okay, now I'm going to do this again, only I'm going to use 3 magnets. And I wasn't sure what would happen. I thought there might be too much friction for the 3 magnets, but it looks like the 3 magnets are also following the isopotential lines. And so I made another video like this, where I'm overlaying the isopotential lines in the video image just to show. Now this is one of the reasons I wanted to do this, was I couldn't really tell which way the tiny magnet was orienting itself as it was going along the line, but clearly with the 3 magnets you can see that the 3 magnets are always aligning themselves orthogonal to the isopotential lines. So they are aligning themselves, if you can, hopefully you can see these little dash things in the.
And again, the lines are just a representation of the force, so of course gravity will always be it's consistent. So what's the argument? But I mean, this is just a completely artificial overlay. Yes, there's a mathematical curve that the magnet will take based on its initial velocity. And the argument is what? That there's some other force acting on it? So the only forces you have acting on it are the slope of the table and the initial velocity you put in. And as long as those remain consistent, you'll get a consistent path. But push it a little harder, and that won't stay on that path.
Video image, which are basically this is how iron filings would line up in this magnetic field if we threw iron filings onto this paper. And so you can clearly see.
So yes, you can clearly see you did this one time, and you keep playing it as if they're different experiments when it's just one experiment.
See that these 3 magnets are always lining up.
Always, because you're repeating the same experiment over and over and over. Yeah, okay. Never mind. So I don't know, this is getting a little bit tedious, so maybe we'll move on to the other video, and before I fall asleep or something. So anyway, and do some Ken Wheeler fun.
Conjugate magnetodielectric field of the magnet itself, but there's nothing located there.
Oh, okay, there
it is the pressure mediation necessitated of the energy emission and the magnetodielectric geometry of the torus and the hyperboloid mediating out their own pressures. Everything in nature, of course, is pressure mediation.
Okay, there's something that I really want to insert in this.
Right, so he should have keyed on everything is pressure mediation, because really that's what it is, right? And it's water has a different pressure than oil, whatever, however you want to look at it. I mean, there has to be something in here that creates this inverse reaction. So, in my opinion, there's no other way to do it. You have to have 2 kinds of force. There's no way to make one force, push something away and in some way give something opposite negative momentum. Making a negative momentum force wouldn't make any sense. I mean, it wouldn't be at all. There's no indication of any negative momentum force in anything we see, so it just doesn't make any sense that there can be anything called negative momentum.
Video, and this is probably the best place for it. Ken says that everything in nature is pressure mediation, whatever the fuck that means.
Well, I mean, that's not that complicated, is it? I mean, you really can't. That's not that hard to figure out, right? That you're changing it. You go from low pressure places to high pressure places, and you're really just saying what is the sensor sensitive to. So again, I could just make it all red and blue light, and I could say if all there was red and blue light, and I could sense it. I can sense how much blue there is, or I can sense how much red there is, and based on how much there is, I could come up with some sort of definition of the differential between the two, and say that's pressure mediation.
Ken claims to be one of the only people to truly understand the universe. Now, I don't want anyone thinking...
Right, so that's an interesting claim, it's fine, but the fact that he is completely unwilling to defend it against challenge is the part where, well, if you're so sure you're right, Why are you afraid of any interaction with any adversary whatsoever? There's no evidence that Ken Wheeler has ever debated anybody who interrogates or tests his physics. He just runs away from anybody who wishes to test it and to see if it's got a flaw in it or something incomprehensible in it. I mean, people who know aren't cowards. I'm sure if I challenge Ken Wheeler to debate Palladian, Sanskrit, Doodah, whatever the languages he thinks he knows how to decipher, he'll love the challenge. He'd love it if somebody made a video saying, you're wrong in your interpretation of blah, blah, blah. He'd probably just love that. But why is he such a coward on the subject of magnetism?
That I am shitting on Nikola Tesla. I have huge admiration for the man. I actually want to bring up...
So that's kind of a bizarre thing, right? Huge admiration for Tesla. I mean, Tesla is just... There's just no way to look at him except for a mixed bag. That's it. You know, and he's clearly, you know, in some respects you can say after the age of 27, you know, he sort of just lost it. You know, 37, whatever. The whole rest of the time he was here, it's like he learned all the wrong lessons. Because, yes, the rest of his life was mush.
A quote by Tesla, which makes me smile every time. And this quote is that, if you want to find the secrets of the universe, think in terms of energy, frequency, and vibration.
Right. So there's 3 words there, right? If you want to understand think in terms of energy, frequency, and vibration. Now, I'd argue that, you know, the word energy is just, that could be pressure mediation, right? You know, how compelled are you to go this way versus how compelled are you to go that way? Just, that's what's happening with gravity, right? I put something at that right location, you know, between the Earth and the Moon, and it's not compelled to go anywhere. Well, it would be wrong to think it's not compelled because nothing's interacting with it. It's clear that it has an equal, okay, amount of interactions going one way as the other way.
Firstly, I find this quote really funny because the electric universe proponents love Tesla and this quote, but they rail against quantum mechanics, even though quantum mechanics does exactly that.
All right, that's the joke, right? It doesn't do exactly that. It has weird entanglements in it. It has these virtual photon that doesn't make any sense. It's a negative momentum. You know, so whatever. But the whole idea, where in a magnet is there a frequency, right, or a vibration? So where do you come up with that? Where is there any indication a magnet needs to function based on a frequency? A static magnet. What's the frequency? What's creating any frequency or vibration? It's non-existent. There's no evidence there's any necessity for anything called a frequency or a vibration. It's just babble that there's anything essential. And magnetism is one of the most essential forces there are. And the same thing with 2 charges moving towards each other. Where's the frequency? If I just put electron and proton and they move towards each other, where's there any dependency on anything called frequency or vibration? There's none.
Tesla was absolutely right with this, and I don't think he fully understood exactly how right he was with this. A more concise statement...
So that's pretty pretentious, right? Oh no, Tesla didn't even know how right he was. Hilarious.
would actually just be, if you want to find the secrets of the universe, think in terms of energy.
So that just means so little, right? I mean, the word energy just doesn't mean anything, you know, in terms of being explicitly defined. I mean, I would argue the explicit definition is, you know, imbalance. You have to have more of something and less of something else. You have to have low pressure one side and high pressure on the other side, or you're not going anywhere. Period. That's energy. So energy is where there's imbalance. Period. That would be my statement. But to say the word energy as if everybody has the same definition of energy is just kind of a joke.
This includes the frequency and vibration bit as well. The point here is that if you want to understand...
So, again, it doesn't include any frequency and vibration. There's no, like I said, magnet is... There's no evidence that... yeah, magnet not quite strong enough. Anyway, that trick didn't work. But there's just no evidence that there's any frequency or vibration that would pull a piece of metal into this magnet. There's just no evidence of it.
the general trends of any physical process anywhere in the universe, you just need to consider one simple statement. The universe is lazy. All objects want to be in the
Okay, so again, this is the part that, so again, this is just has to do with the fact that they don't think there's somethings, okay, and that the somethings are moved by what's called force. So I would argue the simplest explanation is if something's moving the speed of light, it's called a force, okay, and all the stuff not moving the speed of light is some other kind of matter. And the stuff that it doesn't exist, of course. But, I mean, it's clear that the matter only moves because force tells it to. Not empty space, not nothing, not bullshit. No, a force tells it to. There's more force on one side than the other side, then it moves. There's more force, blah, blah, blah. And the point is that the catch is that there's oil and water force. There's red and blue force. There's two kinds of force, and they inversely affect electrons and protons, and that's why electrons and protons go exactly the opposite direction in the same stream. One of them goes upstream, one of them goes downstream. It's not because that they interpret the stream differently, it's that the stream is actually different to them. There's two streams, and one is affected by one kind of water, and one of them is affected by the oil, and inversely. Blah, blah, blah. Everything's push, okay? And it's just that the fact is you can take away push, and that ends up looking like a pull.
lowest accessible energy state. And that is physics in a nutshell.
Says you. And based on what? And those were just such trivial declarations or statements in terms of their don't say anything explicit. They don't say anything specific. They're just so general as to be absolutely like saying nothing. Air is airy. Physics is energy-ly. Yeah.
I'm going to cut this here and wrap up. For the rest of the video, he talks a bit more nonsense about stuff that has nothing to do.
Right. Well, I think you do some of that also. So, anyway, enough of a video. Was hoping to be a little more concise, but didn't really work out. So maybe next time. Blah, 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 blah. And such.